So I'm going to talk about some questions this morning about Toeplitz matrices and determinants. That'll be the focus of this morning, and then in the other talks, some of the other topics. And I'm going to really start as if you have not seen this before. So let's just begin. So a finite Toeplitz matrix has that structure. It's an n by n matrix. It has constants running down all the diagonals. And usually the entries correspond to the coefficients, Fourier coefficients of some periodic function defined on the circle. But actually, you could consider these for any infinite sequence whatsoever. But our focus will be always from the Fourier coefficient approach. So you have a function, you take the Fourier coefficients, you generate these, and the question is, if you take the determinant, what happens is the size of the matrix gets large, so as n goes to infinity. Such matrices occur a lot in mathematical physics. Originally, they were considered for, or one of the original motivations was the two-dimensional Ising model and computing correlations there, but they arise in random matrix theory and in other places. And I hope we'll see some of that as time goes on. Okay, so the second question that we'll tackle, and this is maybe in some sense slightly more related to the Painlevé equation connection, is if you take an integral operator on a line segment, and think of right now as the line segment is finite. So we just have k of x, a function on the line, continuous. It actually doesn't even have to be that. It could be just bounded for what we're going to do. And it just takes a function and multiplies it by k of x minus y and integrates. So that function, k of xy, which is little k of x minus y, is called the kernel of the operator. And now the question is, what happens to the Fredholm determinant? So I'll give a definition of this later in the slides, if you haven't seen it before. But what happens to the determinant of I minus lambda t? And now we want the size of the interval to increase. Okay? So that's the second question that we'll think about. And it turns out that really you can answer both of these questions in almost exactly the same way. So the same technique that works for one works for the other. And so what I'm going to do this morning is show you how to answer, in the beginning, the Toeplitz case, because it's a little bit easier to think about. And then later we'll actually look at the integral operator case as well. And please ask questions if anything is not clear. Okay, so if you're thinking of these finite matrices and you're letting n go to infinity, it's sort of natural to say, does the answer to that question have something to do with the infinite array? I mean, why not just get rid of n altogether? And so the answer to that is, yeah, in some sense that is true, not quite. But so we want to just look at the infinite array here. Let me see if is this my pointer? I'm not sure this is pointing to anything. Oh, okay. Anyway, we want to look at the infinite array and think of it as an operator on a Hilbert space. And there's lots of ways to do that. And what we're going to do right now is absolutely maybe the most natural thing to do. But actually, sometimes you want to do other things as well. So I'm going to say some very simple things in the next slide. But it's important to remember that you're picking that, because a finite matrix doesn't actually care in some sense, about the Hilbert space. You can use whatever you like. So what we'll use is the most probably natural setting, and that is to take just the generalization of Euclidean space and to look at little L2. So we're just going to look at sequences that start at 0 and go to infinity that are square summable. And you can always identify those sequences with the Hardy space. So how you do that is you just take the f sub k's and you form a function, f of e to the I theta, which is just the sum from k equals 0 to infinity of f sub k e to the I k theta. So that's a function defined on the circle, and f sub k is the Fourier coefficient, which is just defined by integrating e to the minus I k theta. So that's a natural setting, and you can actually think of that infinite matrix as just operating on the sequence by just multiplication, just regular old multiplication the way you do matrix multiplication. Okay, so you've probably seen H2 or little L2, but just in case, you have an inner product, which is the standard one. A norm is given by just the square root of the sum, the square of the sequences. And every function in H2 has an analytic extension into the interior of the unit circle. So you just think of that same series, but you just think of the absolute value of z to be less than 1. And we'll go back and forth with that. So sometimes we'll think of the sequence, sometimes we'll think of the function that is analytic in the interior of the disk. Okay. Okay. So now what I want to do is realize that Toeplitz operator, the thing that is infinite in two directions, I want to just describe that some other way. It's not just the infinite array. So we need a couple of definitions. One is just the projection of L2 onto H2. So what does that projection do? It just takes a sequence from minus infinity to infinity, so your entire Fourier series, and just cuts it off and goes, all you do is just go from 0 to infinity. So you have an L2 function onto H2. And we're also going to think about a P sub n, which takes the series in H2 and projects to just the first n Fourier coefficients, so just chops everything off. So these projections we'll use all the time to set things up. Okay, so this is the other description of a Toeplitz operator. So instead of just thinking of that infinite array, we can say, take a function that's bounded, and take a function that's bounded, and the Toeplitz operator with that symbol, that function's always called the symbol, which operates on H2 back to H2, does the following. It takes a function f, that is a function in H2, multiplies by phi. So when you multiply a function in H2 by a bounded function, you get a function back in L2, because the Fourier coefficients may not vanish for negative index anymore. So what you do is just chop those off. So you just apply the projection. So the Toeplitz operator takes a function, it's just multiplication followed by projection. Okay, and to make sure that this is the right thing, if you look at the matrix representation with respect to the standard basis, so I don't think I'm getting this thing here to work. Anyway, if you take T of phi and apply it to, say, E sub k, E sub j, which are just the standard basis for H2, and you just do the simplest computation and integrate, you can easily see you end up integrating phi times e to the I k theta times e to the minus I j theta, because you're taking the conjugate, and that's phi of j minus k. And that says if j minus k is constant, that you have the same diagonal, so it's exactly the right matrix. We just want to make sure this is the right thing. Okay, so that has the right matrix representation. Okay, so once we have that, we need to define one more operator in what follows. And this is what we call a Huncle operator. And it has a actually a very different matrix representation. It doesn't look so different, but it is actually a very different operator. In its index form, it's phi sub j plus k plus 1. And as you can see, it has constants running down sort of the opposite diagonals. So you have A1, then A2, A2, A3, A3, A3. Huncle operators and matrices have been around for decades or maybe centuries. And it's going to be important in what we do. So there's two things I want to mention about this before we go on. The first thing is, if your Fourier coefficients vanish for index 1, 2, 3, and so on, this operator is 0. So you have to have some positive coefficients for this thing to not be 0. The other thing is, let's pay attention to how many of these coefficients we have, because it's going to be important. So we have 1 with index 1, and 2 with index 2, and 3 with index 3. And we'll see that that turns out to be a useful thing to observe right now. Okay, so that's the Huncle operator. And why is it important? It's important because it's one of the fundamental sort of blocks in the algebra of Toeplitz operators. So here are just the very, very basic properties of Toeplitz operators. T of phi is bounded. This little computation at the bottom shows you that. It's pretty trivial to show that. So you just take the norm of T of phi of f, and that's just the 2 norm of P of phi of f, but the P doesn't matter. You can pull out the infinity norm of phi, and that's all you have. Actually, the actual norm of it is the infinity norm. We don't need that. We just need to know it's bounded. And of course, it's linear with respect to A of T of phi plus B of T of phi is A of phi plus B of phi, or psi, sorry, psi. And if your function is identically 1, then your Toeplitz operator is the identity operator. That's all obvious. And then properties D and E, I'm not going to prove. You can try to you just write that out, and it falls out. But it says the following. Property D says if you're taking T of a product, it's equal to the product plus this leftover piece, and the leftover piece is a product of 2 Huncles. And as we'll see, that's going to be useful. And you can also talk about a Huncle of a product, and it splits into 2 pieces. So h of phi psi is T of phi h of psi plus h of phi. T of psi tilde, that tilde just takes e to the I theta and turns it into e to the minus I theta. So it just flips, all that's doing is flipping your Fourier coefficients. So that D and E are basically algebra computations, but just believe them right now. They're going to be useful. Okay. All right. So now I'm going to tell you the answer, and then I'm going to prove the answer. So the best, absolutely the best known result about Topless determinants is the Strong-Zago limit theorem. And in order to get kind of the most useful setting, it's not if and only if, but it's the most useful setting, we're going to look at a Banach algebra of functions. So this is a Banach algebra of functions defined on the circle, functions defined on the circle. They're continuous functions. And they have the property that their Fourier coefficients are summable, and that the sum of k, phi sub k, in absolute value squared, is also summable. So both of those things have to be summable. Those are, if one works, the other doesn't necessarily, either way. So you need both those conditions. And this is for what we will do it's a really nice Banach algebra. And a hint of that is, remember that Huncle operator with the A1, 2 A2s, 3 A3s? That second sum there has something to do with that Huncle operator in some sense being small. So that's coming in a couple of slides, but that's one of the main reasons. But this is a Banach algebra, it's closed. The functions are automatically continuous because of the L1 summability of the phi sub k's. And so if you multiply two of these, they have the same property. If your function, if you take a function in this algebra and exponentiate it, it has the same property. If you have a function that doesn't vanish and has winding number 0, and you take the logarithm, it also has to be in this algebra. And that's also important. So any algebraic thing you can do, if it doesn't vanish, the inverse has to be in this algebra because it's a closed Banach algebra. Okay.
Excuse me, a very naive question. So if I were to take, so the norm is two sums. If I were to take only one of them, it would not be Banach algebra under pointwise multiplication. Is this right? If I took just the first sum of the
I've got to think about that. I think I'm not quite sure. I think if you took just the first one, it's okay. Yeah. Yeah, no, right. But you, right, we need both of them, and they're not the same set of functions. Yeah, I think with the first one, it's okay. Yeah. Okay, so now, here's the answer. Okay, so d sub n is just going to be the determinant of t sub n. And what the Szego theorem says is that the determinant is asymptotic to g of phi to the nth times e of phi as n goes to infinity. And here are the two constants. G of phi is e to the log of phi, e to the 0th coefficient of log of phi. And if you look at, that makes sense, because if you read the top line, it says the function phi does not vanish and has winding number 0. So we know that its logarithm exists, and it has the same properties. You can take the 0th coefficient. The second term is e of phi, and that is the determinant of t of phi inverse. So phi inverse exists. You can take its Toeplitz operator. And so we are taking two Topless operators, multiplying them, and taking their determinant. Now that determinant is actually an infinite determinant. And so here's the way the infinite matrix gives you an answer for the finite one. But it's not t of phi itself. You have to adjust things. Okay, so it's not clear that that last line even makes sense. What does that mean, the infinite determinant? So let me tell you, I'm going to tell you what that means, and then as soon as you know what it means, the proof kind of falls through. Okay, so we have to define this constant. We have to talk about infinite determinants. And so we're going to talk about trace class operators. So trace class operators satisfy a condition that says if you take any orthonormal basis, and you have to be able to take any, that if you take tt star to the 1/2 and take the diagonal of that, that sum has to be finite. And so that's the definition. But the fact is, this definition is hard to check. It's not something that's easy to check. So they're a nice class of operators, but what we want is an easier way to check. So what we're going to do is talk about Hilbert-Schmidt operators. And Hilbert-Schmidt are the things that are kind of easy to deal with. So an operator is Hilbert-Schmidt if you take the absolute value of its coefficients in the matrix array, square them and sum them, and take any choice of orthonormal basis. If one is finite, they're all finite. And the sum is independent. So this is called the Hilbert-Schmidt norm. Okay? So this is a very nice, easy to check, because if you have the matrix array, you can more or less look at it. And the product of two Hilbert-Schmidt operators is trace class. That's what is nice. It's like having two L2 sequences, you multiply them together, you get something that is L1. It's the analog of that. Okay. So we'll worry about these two classes of operators. And here's some properties of trace class operators. These are well known, and they make everything easier. So they form an ideal in the set of all bounded operators, and they're closed in their own norm. Hilbert-Schmidt operators also form an ideal, and they're also closed with respect to the topology defined by their norm. As I said, the product of two Hilbert-Schmidts is trace class. If T is trace class, then T is compact. These are all limits of finite rank operators in these separable Hilbert spaces in their particular norms. So they have discrete spectra. And if they have, say, discrete spectra lambda sub I, because they're compact, and the eigenvalues are L1 summable. So that's what follows from the definition of being trace class. That fact E there, allows us to write down an infinite product that we're going to define as the determinant. So if your lambda i's are eigenvalues of your operator, and you add 1, or the identity to it, then those eigenvalues should be 1 plus lambda I, right? So that infinite product then makes sense, because your lambda i's are in L1. So that's the definition of an infinite determinant, or it's one way to do it. Okay, and then another thing that is really useful is if you take an I plus T, where T is trace class, and you project, you apply the P sub n, where that's any set of actually orthogonal projections. They could be finite rank, they could be not. And if they are finite rank, we always think of the determinant defined on the image of that, right? So that will converge to the determinant of I plus T for any set of orthogonal projections. Property H is another useful property. If an goes to A, strongly, that just means pointwise. That means an of f goes to a of f for any f in your Hilbert space. And bn star goes to b star strongly. Then if T is trace class, ANT Bn converges to ATB in the trace norm. That's what we need. And the functions defined by the trace, which makes sense, and the determinant are continuous on the set of trace class operators and with respect to the trace norm. So all of these are basic facts about these operators. If T1, T2, they don't have to individually be trace class, but if the product is trace class and T2, T1 are trace class, then the trace of T1, T2 is the trace of T2, T1, and the determinant of I plus T1, T2 is the determinant of I plus T2, T1. Okay, so if you think about ordinary determinants, everything that works there basically works here. You just have to be in the right setting to get things to work. Okay? All right, so we want to apply this. First of all, we want to say the constant in this theorem makes sense. The constant in the Zagel limit theorem. So remember, everything is supposed to be in our Banach algebra, right? So phi is in our Banach algebra. It doesn't vanish, so phi inverse is. So T phi psi is T phi T psi plus H phi H psi tilde. That's one of our conditions. So if you let psi be phi inverse, then you apply this, you just get T phi T psi inverse is I minus H of phi. Sorry, T phi T phi inverse is I minus H of phi inverse tilde, right? And each symbol is in the Banach algebra. And what is the Hilbert-Schmidt norm of one of those operators? Well, those are the Huncle. So remember what they do. You have 1A1, 2A2s, 3A3s. You square them, you add it all up, and you get exactly that sum. So if you're in that Banach algebra, then both of those Huncle operators are Hilbert-Schmidt. The product then is trace class, so that determinant makes sense. So that's the first thing. We have to have the answer make sense. Okay? Is that okay? Yeah? Okay. All right. Okay, so now the answer makes sense. So now let's actually prove the theorem. All right, so I want to make another remark about these identities. So these two algebra identities, which are building blocks of everything we do, also tell you two other things. If you have a function psi minus or psi plus, so these, if they have the property, say for psi minus, that for k bigger than 0, they don't have any Fourier coefficients, they all vanish, or for psi plus, for k less than 0, the Fourier coefficients vanish, then you can pull out those Toplitz operators. And why is that? Well, think of that top thing with psi plus on the right. So if you look at t of phi t psi plus h of phi h psi tilde, if you have a plus function, the tilde changes it to a minus function because the Fourier coefficients flip. So that doesn't have any then positive Fourier coefficients. So therefore, h of psi tilde is 0. And the same thing on the other side. So you can factor out a minus function on the left and a plus function on the right for Toplitz operators. And you can do a similar thing for the Huncle, except they both involve minus functions actually. You can factor out a minus function on the left, and phi plus tilde, you can factor it out as psi plus on the right. I hope I had the rights and lefts straight because I mix those up all the time. But anyway, yeah, minus on the left, plus on the right for Toplitz. Okay, and that just follows from that identity. All right. Okay, so now let's continue with what I hope is the proof of this. So if phi sub k is 0 for k less than 0 or k bigger than 0, then the Toplitz matrices are triangular. So now I'm talking about the finite Toplitz matrices, right? Because the positive Fourier coefficients were below the diagonal and the negative coefficients were above the diagonal. So you just have something that's either here or here. So the determinant is trivial in that case. The determinant of Tn of phi is just the 0th coefficient to the nth power, because it's triangular. Okay, the other sort of obvious but observation we want to make is that the finite matrix is just the upper left corner of the infinite array. So if you take the whole array and you just chop it off like that, you get the finite matrix. Okay. Now, here's a crucial algebra step that makes this all work. If I have chalk, is there chalk? Yeah. Let me write this out because it's important. So if U is an operator whose matrix representation is upper triangular, so if you have something like this, so ours Toplitz ones look like this, right? So if it has an upper triangular representation, and this is all 0, right? And we apply a p sub n, what that's going to do, so all of this is 0, is it's going to make this all 0. So if you cut it off like that, it's the same thing as having a p sub n on both sides. Okay? So because if this all becomes 0, this is already 0, and it's the same thing. Okay, so that's crucial. And if you have a lower triangular form, something over here, and you cut it off this way, it's the same as cutting it off both ways. So that fact is what allows you to have an absolutely simple proof of the Zago-Witten theorem. Okay, so you only need one of the p sub n's in this case. Okay, all right, so if you had an operator and you could factor it into lower triangular times upper triangular, cut it off, you could move the p sub n inside, and finding your determinant would be absolutely trivial. Okay? So that would be wonderful, but that doesn't happen. What happens for Toplitz operators is the opposite. It doesn't factor into L times U, it factors into something that's U times L. So it does just the opposite of what you want. So what are we going to do? We're more or less just going to fix that via a commutator. Okay, so now we have to talk about something called the Wiener-Haupt factorization of the function. Okay, so our function lives in this Banach algebra. It doesn't vanish, it has winding zero. It has a logarithm. If you take the logarithm of it, okay, imagine taking the logarithm, you can split it into a piece that has positive coefficients plus a piece that has negative coefficients. You can exponentiate that back, and what you're going to have then is a product of something with positive coefficients and possibly zero times something with negative coefficients. It doesn't matter where you put the zero term in either factor. Okay, so we have this Wiener-Haupt factorization which allows us to write our function phi as a function with negative, possibly zero coefficients times a function that has positive Fourier coefficients plus possibly zero. Okay, so phi plus extends to be analytic inside the unit circle, and phi minus, because you're just replacing z by 1 over z, extends to be analytic outside the unit circle. And this is true also of these inverses. As long as we're in this Banach algebra, whatever holds for anything that is legal will hold for everything. Okay. All right. So we have that factorization. And then we look at our properties again. Remember what we said. If you have a plus function, you can factor it out onto the right. So t of phi is t of phi minus times t of phi plus, if you have this factorization. Okay, but what does t of phi minus look like? It has coefficients above the diagonal. T of phi plus has coefficients below the diagonal. So t of phi minus is upper triangular. T of phi plus is lower triangular. So that's the splitting we have. It's not quite the right one. It's the wrong order. So, but we're still going to make use of this, and this is what's really crucial. Okay, so here's how this goes. You take your Toeplitz operator, t of phi, you truncate it to get your upper left-hand corner, and then you split that function apart. And now we have upper triangular times lower triangular. And what we're going to do is insert more or less the order we want on the outside. So we're going to put a t of phi plus times t of phi plus inverse. Those cancel because they're plus functions. And t of phi minus times t of phi minus inverse, those cancel because you can always bring minus functions in from the left. So we haven't changed it. But now, what we can do with that p sub n is bring it inside, because of that property that the t of phi plus is lower triangular, so the pn will come inside, and on the right-hand side, the pn can come inside one step. So this is just basic linear algebra. Okay, now if you take determinants, think of taking determinants of that whole thing with respect to the finite matrices. The determinant of the t of phi minus is just phi minus the 0th coefficient to the nth power. For the t of phi plus, it's just phi plus the 0th coefficient to the nth power. That's all it is. So we've got that. Okay, what's left is the middle. Okay, so the middle has the Pn and has 4 operators. But now we're going to use our algebra again. If you take, say take the two on the two most left ones, t of phi plus inverse times t of phi minus, use your algebra property and collapse those. It'll be t of phi minus over phi plus 2 huncles. But what are those 2 huncles? You're in your algebra, so those huncles are trace class. The same thing for the 2 operators on the right. That's going to be phi plus over phi minus. Collapse those. We can always collapse. We have then that Toplitz plus Huncle. But now collapse again. I mean, if you multiply those 4 functions together, what do you get? You get 1. So with repeated collapsing, you always have something plus trace class, something plus trace class, and eventually I plus trace class. And remember, it's an ideal, so you always can multiply, and you're still in trace class operators. So this is of the form I plus A, where A is trace class, and then we just use the fact that the finite determinants converge to the infinite determinant, and that converges then to this determinant of the product. But we can take the t of phi plus inverse and move it all the way over, because it's just a standard property of determinants. And so it's a little bit easier to write it the way you have it there on the right. Determinant of t phi inverse. Collapse them again. So that's it. You just set this up correctly, and then there's sort of a 3-line proof, and everything works. Okay. So the assumptions are phi has to be in the Banach algebra, winding number 0, can't vanish, winding number 0, and you've got your theorem. I'm sorry. Second term. Yeah, you can, I'm going to say something about that, yeah, in a second. Yeah.
So excuse me, I got confused. Where have we used the sum of absolute value? We have used the Sobolev norm converges, but where have we used the sum of absolute values actually?
Well, we're starting with, we want a continuous symbol, and we're starting, if we just have that Sobolev norm, we don't have the Banach algebra. We're using that over and over again. Right, yeah, right. Yeah, just in the Banach algebra part, yeah. Was there another question? Yeah, so we'll talk about, we'll actually talk about an identity instead of this in a second. But let's stop here and go on. Okay, I just want to rewrite this because this is not the original way that Zago wrote the answer. So how do you get the original answer? So again, if you take this operator and you write it as t phi minus t phi plus t inverse phi minus t inverse phi plus, you can do that because for the plus and minus functions, inverse and commute with the Toplitz part, then this is you can rewrite this as e to the a, e to the b, e to the minus a, e to the minus b, where a is t of log of phi minus and b is t of log of phi plus. Okay, so that's, again, just simple algebra. But there's a formula for such a determinant. Comes from the Baker-Campbell-Hausdorff formula. So the determinant of such a product is the exponential of the trace of AB minus BA. So I gave a similar talk once, and then someone told me at the end it was trivial because the trace of AB minus the trace of BA must be 0. So so I was being really, silly. But AB minus BA in this case is trace class. It isn't the fact that AB is trace class. You have to take the difference. So So there really isn't, this is really right, there really is an answer. And if you simply take that trace, you get this sum here. You get the exponential of k of the sum from k equals 1 to infinity of k of log of phi sub k, log of phi sub minus k. So this is Szegő's original answer. And just notice that this is never 0. And he was actually, the first case he did was for a real valued function. And in that case, this is actually the log phi minus k, that product is actually the absolute value of log sub phi of k. That sum is actually positive. Okay, so that's the answer. Okay, so we've got an answer, we've got our proof. And so what I want to do is talk about now adapting this proof, or I just want to tell you how you can adapt this proof. So this, you know, if you have a proof that is nice for one thing, but never works for anything else, maybe it's not so great. But this proof actually works in a whole bunch of settings. And the real essence is you just multiply on the right and left by something that makes the middle thing trace class, or I plus trace class. That's really the moral here, the lesson. And so it extends to lots of other things. And so let me kind of go through that list. So the same proof works almost word for word for matrix valued symbols. I haven't talked about matrix valued symbols at all here, but instead of constants running down diagonals, you can have a matrix valued symbol so that the things on the diagonals are actually matrices themselves. So you're actually getting periodic diagonals then. So the same proof works, except that you have to have a two-sided factorization. I mean, you have to be careful about order. So it's a little bit different. And the other thing about the matrix case is that last computation I did, where I wrote it in Szegő's original form, does not work because things don't commute the right way. The actual scalar functions don't commute. So in the matrix case, it's hard to figure out the answer, the actual answer. I mean, an infinite determinant is an answer, but it's maybe not an answer that you know a lot about. And in the matrix case, the answer can actually be 0. And you can't even tell ahead of time sometimes. So the matrix case, there's a ton of work in some sense still to do. There is some stuff known, and we could talk another whole hour about the answer, just the answer itself in the matrix case. Now, this same proof also works to give you an identity for Toplitz operators. You have to use one more sort of little fact, and it's something that's called a Jacobi identity for projections. It's an old thing about determinants that everybody's mostly forgotten, but if you use it for this, it works. And it says the following, and this helps answer the other question about other terms. This is not asymptotic, this is equals. So given the conditions of our theorem, the Topless determinant is equal to the geometric mean to the nth power times our constant E of phi, which is a determinant of T phi inverse, times another infinite determinant. But this infinite determinant is I minus a product of Huncles, and Z here is e to the I theta. And what each of these Huncles do is tend to 0 in the Hilbert-Schmidt norm. And what happens, well, it's not quite right. Those are Hilbert-Schmidt matrices, actually times projections that are tending to 0. And so that term tends to 0 in the trace norm. So if you like, you can try to expand this and get other terms. That's one way to try to do it, and sometimes we've done that. So this is another way to prove Szegő's theorem. You just say that the Hilbert-Schmidt norm or rather the trace norm of the product of Huncles tends to 0, so that determinant tends to 1. So this is an identity. This identity was done independently by 2 different groups of people. Case Geronimo did it a long time ago in sort of an appendix of a paper, and no one knew about it. And then Borodin and Okunkov did it because of some random matrix theory problems. It was sort of rediscovered and now been redone in all kinds of settings. Okay.
You have 1 minute.
I have 1 minute? I thought I had till, no, okay. All right, so, yeah, that's fine, okay. So it can also be adapted to this case, and this is actually sort of new. So if you take your Topless matrix, and if you have an analytic function, say defined on a disk that that's as large as the norm of the function, the infinity norm, then you can take f of t of phi, and you can you can truncate that operator. Have no idea what the matrix representation looks like, but you can ask about the asymptotics of its determinant. And you can do the same proof, and here's the answer. It's the geometric mean applied to f of phi times the determinant of f of t of phi times t of f of phi inverse. So the very same proof works. And it works in the matrix case. And sometimes you get sort of interesting answers out of this. It can be adapted to perturbations of a Toeplitz matrix. You can take Topless plus Huncle and chop it off, and take the upper left-hand corner and ask about those asymptotics. Or, T of phi plus h of psi even. You can change h. So it's very, very adaptable. Okay, so I think maybe next time I'll start, if I have just about out of time, with the integral operator case. So the next thing I'll start with is adapting, or just showing you why. I'm not going to redo the proof of why this works also for integral operators, because in some sense they have exactly the same structure. It's just different projections, different setting, but it's completely, the proof is completely analogous in the Wiener-Hopf setting. So we'll start with that next time. Just a little word about history. So Zago did what's called just the Zago theorem, which didn't have the constant term, in 1915, long time ago. And then in an answer to a question about an Ising model given by Ansager, extended it to the constant, and I think it was around 1952, and he did it for positive functions that were smooth. And then this became more important in that setting, and then it was extended by lots of people. Whittam extended it to the matrix valued case much later, in about 76, I think. So it's now for with the matrix addition, it's generally referred to as the Zago-Whittam theorem. Okay, I'll stop here and then start up again with the other. Okay.
Okay, so we have. Yes? So questions for Estelle?
Yeah.
Yes?
Oleg. Hi.
Sorry, may I ask you about this Borodino-Kunkov case Geronimo? So, does this identity mean that E of phi, so this constant, is equal to 0 only if the determinant of Tn of phi is equal to 0 for any n?
No. No, not at all. You mean, okay, E of phi, right, is never 0 in the scalar case, first of all. It can only vanish in the matrix valued case.
Formula bears.
Yeah, yeah. But it does mean something that you might be asking me. This formula here. Yeah? Yeah. Okay, so if, so in the scalar case, E of phi is never 0. In the matrix case, it can be 0, and the determinant of T of n of phi still not be 0. What that really means, you're not going to have such a nice factorization in that case. The way to interpret it is the determinant of T sub n divided by G of phi to the nth goes to 0. Just goes to 0. In that case, it doesn't give you any good information. You have to do something more to It's like the scalar case with a lot of winding or something. Yeah, right. Is that what you're asking?
Yes, exactly.
Yeah, right. So, but you can see something out of here. So if it's actually a case where you can figure out E of phi in the matrix case. If those Huncles, if those things, see that that z to the minus n will kill your coefficients if you only have a finite number of them, right? So if your coefficients only go out to, say, index 5 or something, and you multiply it by z to the minus n, those Huncles disappear. And then you can compute E of phi from a finite determinant. And that's a case where you can actually do it in the matrix case. But in general, that's really, no general results exist except for that. Yeah.
Okay. Thank you.
So any further questions? So I just have a quick question.
Yeah.
So this theorem still at the end, sorry, I asked the same question again. At the end, the theorem only requires the finitude of the Sobolev norm. This Banach algebra structure is the artifact of the proof, and then by density arguments or something like this, it can be.
That's right. But it's not if and only if. So
yeah, that was my question.
Right, yeah. So for example, if you have a real valued function. Let's go back to the, whoops. Okay, so if you have a function in L1 that has a logarithm that exists in L1, and you write down the Fourier coefficients, and if that sum is finite, then Zago's theorem works.
Right.
Yeah, that's all you need. All you needed is for the log of that sum. You take the coefficients of the log. So it's for real valued functions with a logarithm in L1, it's sort of if and only if.
And that's an if and only if.
Yeah.
And in matrix case also there is if and only if?
No, there's no, in matrix cases, no. There's no, there's no, matrix case is just much, in some ways it's the same proof. So you think, okay, it's kind of the same, but the matrix case is difficult. And you've got these cases where that E of phi is 0 and then you're just getting nothing out of it. For very simple functions, that E of phi can be 0. Yeah. Is that
yes,
Ken? Yeah.
What's a good, thanks. Could you tell us a good reference for some of the properties at the beginning of your lecture?
The reference for the I actually have these at the end of my slides. You mean the historical properties or just the properties of the trace class things? Or the whole, all of it? Yeah. Is that, yeah?
I figure people, if
yeah, so I'm going to go to the very end of the slides because I have some references done, but then I ran out of time. Okay, so this is all coming tomorrow. Okay, so this is the original paper of Zago in 1915, and then the one that actually produces the constant, which was the the answer to Ansager's question is in 1952. And then there was a huge amount of activity in this field. There's lots of people I haven't mentioned yet that I was going to do at the end. But Albert Bachter and Bernard Silverman did a lot of work in this area, especially for singular symbols, which we're going to talk about later. And they have 2 books, which in some sense have everything you've ever wanted to know about Toeplitz operators. One of them is called Introduction to Large Truncated Topless Matrices, and it is accessible to the non-expert. You can actually open it up and figure out what a theorem says. The other one is Analysis of Toeplitz Operators. It's classic in the field, and it has everything about trace class operators, Hilbert Schmidt operators, all the Banach algebras, all the different spaces, everything. It has all these proofs that I did. Whittam's proof, which was in '76, is the first proof that used sort of operator theory to do this problem. Before it was a lot of identities analysis. They were nice proofs, but that was the beginning, and that's the first place that this infinite determinant was used. And then Harold and I, the Borodino and Kuhnkopf identity thing was done first with different proofs, and then we gave a proof that used the same operator theory techniques in a long time ago, 2002. So, but the Bachter and Silverman books are great reference books, and especially the large truncated matrices. A lot about the spectrum. I didn't talk at all about spectrum of finite matrices, but that's another whole, subject. Where are the eigenvalues of the finite matrices? That's a case where you often want to change the underlying space. You don't want to use H2. You want to use something else. But, we could talk a lot longer. Okay.
Okay, so, and I just make the remark that Seger's first reference here was written when Seger was about 20 years old and was in the trenches of the First World War in the Austro-Hungarian Imperial Army. And we thank our speaker again.